Hello YouTube viewers, welcome to my show Future Friday. In today's episode we're going to take a closer look at Starlink. So let's dive right into it. So how the satellite internet is going to work. So the idea behind Starlink is very simple. It's another satellite constellation, same as GPS, same as GLONASS, and all it's going to do is provide World Wide Web to the whole world. So as you have to understand, as of now, I am talking to you as in mid 2019, surprisingly large amount of people have never heard of internet, have never access to internet. And this is not like limited to India or China, it's in USA also. Like in terms of USA, rural areas have really bad internet and very expensive internet, and on top of that they only have one or two option. In those sort of scenario, the ISP that are providing internet, they really don't care. They're like, what else you gonna do? So at this point in time, the World Wide Web is actually not World Wide Web. It's not covering most of the places. Thankfully, India recently got a very giant boost due to entire country getting 4G overnight. So soon hundreds of cities will directly get into high quality fiber optics. So once we do that, India's condition will improve a little bit, but as of now, India's still, rural areas in India is really bad. Rural area in USA is still bad. In China, you flat out can't access it, and in Africa, let's not even go there. So you have to understand, at this point in time, we don't have a service provider that can say 100% of coverage. So let's say you are in North Pole or Norway or things of like that nature. There are many places where you do not have good internet. So this is the whole idea behind it. So even though, let's say in big cities where you have good internet service, you don't have to change to the satellite system. However, the places where they don't have any services, that alone will make up the majority of their income. Their target cost, as in like how much they're supposed to spend, is around $10 billion. How much they're supposed to gain out of this? That's upwards of $30 billion. Let that sink in, and that's in roughly US alone. So that is the idea about it. Whole planet coverage using satellite constellations. That's the idea. Then we come to the aspect, nobody has ever tried it? No, we have tried it, and we have also successfully implemented it. So the current solution that we have as of now is what we call geostationary constellation. You can check out my video about geosatellites here. Now it works great for one-way communication. Basically, let's say presidents of the United States or governmental party of India or Narendra Modi and these sort of people want to communicate to large amount of people. Geostationary is awesome for that. So one point source of origination that goes to everywhere, that is thoroughly done. We can do it right now. That's what your direct to home satellite dish TV is. This works, it's tested. However, this is one way. That is the biggest problem. It's very great for receiver, but it's really bad for transmitter. So on top of that, this gives you very expensive internet if you try to get internet from it, and on top of that, it would be ludicrously slow and ludicrously laggy. Now to deeper understand why it will be basically laggy, it's simple. It's distance. Now why it would be slow is simply because it has to do something with what we classify as inverse square law. You can check my video about that here also. So the problem is, even if you put, let's say, 100 watt transmitter power, given the fact that your mobile barely has like 1 to 2 watt of transmitter power, you put 100 watt, you can barely communicate to satellite. And if satellite gives out, let's say, even megawatts of power, it can barely communicate to you. And that's happening because of inverse square law. That is physics based. You cannot bypass it. So that is our current solution. It works great for TV, but for everything else, it simply does not work. So is there any better option? Well, yes, LEO option, basically low Earth orbit. Basically, instead of going to 36,000 kilometers, we stay as close to as 5,000 kilometers. Basically, anything below 5,000. And space starts at quote unquote 100 kilometers, quote unquote Kármán line. So if you are above 100 kilometers, you can do orbit, but your orbit won't be stable or for very long. So as you start to go up, your orbit becomes stable and stable and stable. So once you reach around 200, you can tangibly put satellite there and expect it to last. So, and to give you a context of that height, International Space Station is roughly 300 to 500 kilometer, because the orbit is not perfectly circular, so it does have apogee and all that. So LEO has the advantage of it's very cheap and it's very fast. Cheap because rockets don't have to travel to 36,000 kilometers, it only has to travel to 1,000 kilometers. That inherently saves a lot of cost in terms of rocket itself, because you have to use less fuel. On top of that, it's very fast simply because the distance needed is very slow. Even at light speed, going to geostationary and coming back, just that, like you go to geostationary and you come back, that takes upwards of 200 milliseconds. and if you try to do that with, let's say, any low earth orbit satellite, you can barely easily do it in around 20 to 30 millisecond. So anything below 50 millisecond you can do communication, real-time communication with it, because our eyes and ears are designed in such a way that they can handle lag of 50 millisecond inherently. So, and if done correctly, you can drop it down to upwards of 20 millisecond. So it's very thing. However, it does come with a consequence. It requires way too many satellites, because in geostationary you can have only 3 satellites and cover the entire globe. That's the reason why our direct to home TV comes from there, because they only have to launch 3 satellites and done. When you're talking about geostationary, like let's say Iridium Sat or Iridium sort of constellation that are there for satellite, basically satellite mobile phone communication, they require 70, 80, sometimes even hundreds of satellites to give a basically coverage, 100% coverage of Earth. So that is the biggest consequence of this. Everything about LEO is cheaper. Okay, the satellite itself is cheaper. The fact that you basically need you get very high speed internet, that's also awesome. Everything about it is cheaper. The rocket needed to carry basically satellite, that's also cheap. But you need a lot of them, multiple times more of them, like 10, 30, 20 times to sometimes 100 times more. So that is the consequence of LEO option. So what the heck SpaceX is doing here is basically they are going bold, because they have what we call Falcon 9 Block 5, basically this puppy. They can reuse the rocket, and that gives them a very core advantage. You have to understand it from their point of view. They're making a rocket and reuse it upwards of 10 times, and satellites are barely 500 kilograms. This puppy can easily put 22 tons into low Earth orbit, and the payload fairing is big enough that they can have upwards of 10 to 20 satellites per launch. So they got the rocket, and the idea with SpaceX is they're gonna take care of a whole Earth, because there is a consequence, because USA is so high up, as in like it's so close to North Pole. You have to have constellation in such a way that it covers the polar region. That's very tricky. So the way SpaceX is tackling this is they're gonna have 2 independent constellations. The one constellation would be very close to Earth, very close, as in 300-kilometer orbit. That will be very close to Earth. And then there will be another that would be upwards of 4,000, still in LEO, but it will be much higher, and that will be in polar incline. Basically it will go around the pole. This will give much higher coverage in North Pole, South Pole, Russia and Alaska. Alaska was the main reason why they had to do it, because they cannot classify as ISP if they are not covering Alaska, and Canada also gets the benefit of it. So that is why they have 2 independent satellite constellations. Of course they will have cross communication, undeniably so, but the whole idea is that you have the primary constellation which could contain upwards of 4,000 to 7,000 satellite. Each satellite would be upwards of 90 to 100 kilometers apart from each other, so don't worry about collision. And in terms of weight, they will be weighing upwards of 300 to 500 kilogram, and this satellite would be ludicrously cheap because they will be mass produced. You're not gonna make 1 or 2 of them, you're gonna make thousands of them, so it will be produced same as iPhones. And then they're gonna utilize Falcon Heavy. You can check my video about Falcon Heavy here. So Falcon Heavy has this advantage that even though it has the same, more or less same carrying capacity as Falcon 9, simply because of the basically diameter and fairing size, it does have higher basically thrust, which translates to, if they have to send, let's say, 50 satellites to low Earth orbit, this can easily do it. If they have to send 50 satellites to high Earth orbit, as in like not high would we say, but let's say 5,000 kilometers, the Falcon Heavy can easily do it. So this is how they are going to take care of it. And the core advantage SpaceX has is they have very high throughput. So their main target is the fact that they can even think of that we can make a satellite constellation in $10 billion is simply because of their high throughput. As of now, as I'm talking to you, at this point in time, they are the biggest, fastest, most quickest in terms of launch vehicle there is. There is no competition to this, flat out. Not even ISRO can compete against this price. It's that fast, that very quick. So this gives them the idea, like they can literally test out batches of satellite, and they have already done it. I will provide the link down below that they have already tested 2 satellite launch on a primary satellite mission. Basically Falcon 9 was sent for a main mission. On the side on, they tagged on 2 extra satellites just for extra testing. So SpaceX can pull this off simply because they have such a good tested infrastructure. And if BFR comes along, that's a whole different ball game. That may be able to put upwards of 200 to 300 satellite and finally breaks India's record of 120 satellite in one go. So that's what SpaceX is doing. So okay, that's the whole idea, satellite, internet. How does it actually work? Now this is where I want to focus your attention on bands. If you are familiar with internet, you must know you have Wi-Fi, and you must be familiar with the fact that you, in Wi-Fi terms, you have 2.5 gigahertz unregulated, which is basically your normal Wi-Fi, and some people use a higher end basically Wi-Fi equipment that goes upwards of 5 gigahertz. Now the mobile tower that you are using, that's generally working on a millimeter I'm saying microwave range, so it's not very fast. That's why your Wi-Fi is always faster. So what people are trying to do is basically go higher in gigahertz. Basically, how much gigahertz, the higher the gigahertz you go, the smaller your antenna becomes and higher the throughput. So this is a very simple graph that you have to focus on. Basically, if you have 1 gigahertz, the amount of data, basically let's say how many megabyte you can put from one to another, is very low. So as you start to go higher and higher and higher, you can send more megabytes to the other end. And the another benefit becomes is that your satellite antenna, basically your antenna, no matter where you're communicating, your antenna size is directly proportional to the frequency it's using. So all antennas are unique, specifically tailor-made for the frequency. 2.5 gigahertz antenna would be completely different from 5 gigahertz. And when you're talking about, let's say, going higher in gigahertz, your antenna will become smaller. I know it sounds counterintuitive, but it does become smaller. So you can transmit a lot of data, and you can make your antenna smaller. Now also there is another benefit of that. Let's say bandwidth, electromagnetic spectrum is ludicrously wide. It's very wide, like humanly you cannot perceive it. To give you a context, like microwaves are inch apart and light beams are nanometers apart. So like I can't justify it, like how wide spectrum is. Now this gives the advantage that bandwidth distribution, let's say somebody country tells you, okay, you can make your antenna work at 25 gigahertz to 30 gigahertz. They're giving you 5 gigahertz of leg room, basically how much you can go another. Because of the high throughput and antenna size, you can literally fine tune it. Basically, even in that same bandwidth, you can have like 15, 16, 17, 18 channels in them. That is very useful for large communication. You really want to have basically your spectrum, basically how much spectrum you are using, you want it to be as narrow as possible. That's not only saves energy, it also allows you to, like, because no country can license you at like, use 25 gigahertz, that's it, no plus minus. They will always give you at like, let's say 1 gigahertz plus, 1 gigahertz minus. So in those sort of scenarios, let's say you can pack 8 channels. So 8 parallel communication can happen in that spectrum. That is why people want to go higher. However, if everything is so good, why don't everybody use it? It does come with a serious consequence. Higher the frequency, the more vulnerable it becomes, more vulnerable to water itself. Basically, if rain starts to happen, your communication will go away. So that is why not everybody is like going to, let's go to 100 gigahertz. We don't want to do that because it does come with certain consequence. So that is the core aspect why everybody is switching to higher and higher and higher frequency. So the whole idea of SpaceX is they're gonna give you an antenna, and the antenna is supposed to be the size of a pizza box, a big antenna. It's not something you can think of portable, but I think it should be portable enough that you can put it in like size of a laptop and weight of a laptop. So they will be working on V band. Now that bandwidth is from 40 gigahertz to 75 gigahertz, and your Wi-Fi router is barely goes up to 5. So, and they have also targeting other bandwidths, which is KU bandwidth and KA bandwidth, which starts from 12 gigahertz to 18 gigahertz is classified as KU, and 27 to 40 gigahertz is classified as KA band. These are generally how your internet works on your basically airplanes. If you see any modern airlines giving you Wi-Fi service in air flight, they are using this KU and KA band to communicate to satellite. So SpaceX wants to use Starlink to use this also, because there is not enough regulation in these puppy. So they will try to use all these three. Okay, they have hundreds of satellite and they have the frequency. How they gonna communicate from satellite to satellite? This is crucial aspect. They cannot use the radio wave because of inverse square law. The satellite does not have like hundreds and thousands of kilowatt of power. It will be wasted. So what they're gonna use is basically satellite to satellite laser link, and in terms of gigahertz, it will be higher than 10,000 gigahertz because it's in optical frequency. It will basically use laser communication. So you're gonna have laser diodes that will be firing signal and a telescope on the receiving end to receiving it. Of course, they will have duplicate of both basically to have send and receive. That is how they're gonna communicate to satellite, and each satellite will communicate to 4 satellites. So the way the orbit is done is that they're gonna have one transmitter that is directly focused directly forward, one satellite transmitter and receiver directly focused backwards. So because there are many satellites in the same orbit, just like 100 kilometer apart, this will provide the main link A, link B, link C, and then you're gonna have 2 communication that is going side to side. So that way they can directly reroute the communication. Now if that sounds complicated, I have provided a very nice animation and explanation by a very awesome guy. You can check that video out. So basically each satellite will communicate to 4 nearest neighbor, one in front, one in back, one in left, one in right. That's how they are doing it, and that communication is not happening on the radio wave. That's happening using V sort of puppy, and small version of this was tested with International Space Station. So it does work. We know this technology, it does work, and it does allow gigabytes to petabytes of transfer over short links, even in long distance. Like we tried this for 600 Mbps to the moon. So it's tested technology. And then okay, this is how the satellite is working. This is how your basically A to B is happening in space. How the heck you gonna receive the signal? You're gonna have something like this, what we classify as phase shift array. Now, if phase array is too fancy for you, just think of it this way. Phase array is basically like how 5G is supposed to give you higher bandwidth. Basically, the higher the frequency, the smaller your antenna becomes. So if you have a lot of small antenna and you can trigger it in such a way that there is constructive interference and destructive interference, if you time it right, basically you need very good clocks for this. If you time it right, you can literally have a flat antenna that is like flat like this, but the signal, instead of going like this, it can go like this, it can go like this, it can go like this. So you just put your, let's say, pizza box in like a rooftop, your antenna can literally follow a satellite like this. This is how 5G works. This is why people are shifting to higher frequency, because the higher the frequency, if let's say they go to 75 gigahertz, they can pack like hundreds and thousands of tiny antennas, and each will be like allowing you to phase shift. And this also has the benefit, it also removes interference. Basically every transmitter and communicator is directly talking to the satellite. There is no interference. Basically you can take a receiver next to it, it would not work because it's focused so directional. It's basically quote unquote laser kind. So this is how it works, and this is F-22's Raptor nose radar, and this technology was built for radar, and it's now being used for basically 5G communication. 5G mobile towers are like this, and this is why they want to go upwards of 75 gigahertz. Now be mindful, it still works at 12 gigahertz if they have to, but it won't be very efficient. So they really want to go as high as possible. So generally they would be targeting at 60 gigahertz. Now this is all the hardware aspect. You also have to understand our internet is built for a current architecture. Current architecture is you go from your home to your nearest node. That nearest node connects to your gateway, and that gateway generally connects to your server. Now okay, that's a good pipeline, but here's the in space they cannot do that, because if they try to do it, they have to create what we call a gateway. Every few kilometers they physically have to have a gateway. So satellite will receive the signal from your home, then it's gonna send to gateway is gonna process it, and then it's gonna send where it's supposed to go. That's very inefficient. So to combat that, they're gonna create their new protocol, and the protocol they're gonna create is more or less like how torrent works, because every satellite is communicating to other satellites. They really want to allow you to do what we call point-to-point communication. So not every data that you have, let's say you want to go to Shanghai, basically you want to send data to Shanghai, you're doing a video call, the satellite will reroute directly. It won't go like, okay, I received the signal, I'm gonna send it to a ground station is gonna use basically optical fiber, then that goes there, then it's gonna go to another satellite, then that satellite will receive. It's not doing that. It's directly trying to do point-to-point communication. To do that point-to-point communication, basically IPv6 protocol that we use right now simply won't work. So they are building their top proprietary thing right now. As of now they are working on it, but they haven't launched it yet, so we'll find out. This is the software aspect. Do not think your satellite internet, even if it works, of course you will still have www.google.com, www.youtube.com, but it will have completely different backbone, completely different interface protocol and all that. You won't notice this, you're not supposed to notice this. It's for the network engineer, it will be a headache for them. So that's how it's supposed to work. It's gonna have as high frequency as possible, upwards of V band. It's gonna have laser communication from satellite to satellite. It's gonna do phase array for your antenna. Your antenna is supposed to be size of a pizza box, basically big size as a laptop, big laptop, not a tiny one, big laptop. And it's gonna have independent protocol. This is the working aspect of it. Now, are there any risks involved in this? Absolutely. There are 3 core risks involved into this. First risk is Kessler syndrome. Now, if anything goes bad, like let's say one satellite gets damaged and does not maintain its orbit properly, gyroscopes fails, and it ends up crashing into another, because mind you, even though satellite is very small, satellite is like size, basically this size, it's still traveling at very high speed, and it's still only 100 kilometers away from next to one another. So that creates a very tight tolerance. Something bad can happen and the whole area will be littered with space junk. and everything will be destroyed instantaneously because of this ludicrously high density, because they are planning to put upwards of 12,000 satellite. And to give you a context, we barely have few thousand satellite right now, barely, and I'm talking about every country combined. SpaceX alone want to put 12,000. That creates a paradox as in, like, they really have to do very good management. If they don't, this will happen, space junk. And there is one good side. Even if, let's say, that happens, because this is such a low Earth orbit, it will automatically clear itself. Of course, it could take upwards of 10 to 15 years to clear itself. Now then comes to Ajit Pai. The government can simply override him. Basically, government can be like, we don't allow you to have net neutrality. We don't. Let's say China's government is like, you can't sell your receiver here. Or even if let's say somebody smuggles it there, let's say, and it becomes a big enough issue because China wants to create what we call Great Firewall of China. That firewall will only work as long as they work through optical link, because basically China is funneling all the data through optical fiber. It always does that same way. It's like, that's what undersea fiber cable, because every single bit of data that is created in China goes through that optical link. China can put their firewall right there. Now, when you are talking about satellite, there is no firewall possibility because it's point to point. So you can talk to one satellite and it goes to another satellite. So China has to block it. China will simply say, you can't sell your equipment here. And even if, let's say, somebody smuggles it, or let's say Elon Musk makes it open source, so somebody makes it in their home, because China is capable of doing that. Like, if people can clone iPhones, making a phase array is not that difficult, and they have Hawaii, so they know how to make phase array equipments. 5G equipment is more or less the same. So let's say they start making, China will basically directly interfere with the satellite, and it is doable. They only need a few satellite, basically free ground station directly beaming into the satellite to cause interference. It will not work. Or India can simply say, we can't control internet. If you are using this, flat out you can't use that. So government is a very serious regulation. So people who are hoping for net neutrality and all that, temper your expectation. It can happen, undeniably so, but be mindful. It is a very serious, real threat. On top of that, earlier I used to think there is only one other company that is trying that was Google and Facebook. But here's Jeff Bezos is also working for it. Here's the Virgin Galactic is also working on this. There is a lot of competition in this regard, including Boeing. So Boeing, Jeff Bezos, and Virgin Galactic, Richard Branson, basically a lot of people are throwing their money into this. So if things work out, by 2030 we may have upwards of 2 to 3 satellite constellation for our internet. That would be a very good thing, because if there is only one satellite constellation, government will focus thoroughly on it and completely cripple it. Once we have enough competition, companies can do underhanded tactics, like our encrypted survey. We don't know what people are doing, but if you have only one, it gives a governmental body like him a lot of power. If there are multiple providers, that allows a lot of competition. So there are risks involved into this. Do not think it's a cut and dry situation. Things can go wrong, and they can go really wrong. In case of Kessler syndrome, government regulation can flat out kill it before it even gets off to the ground. And be mind you, because they still haven't got absolute clarity on which frequency they are allotted, because there are other companies also vying for that V band, Ka band, and Ku band. So there is a lot of friction there right now as we talk to you. So this was my presentation on SpaceX, Starlink, basically internet project. I hope you liked it, learned from it. In that case, please leave a like and click the ad shown in this video. That will directly help me. And if you didn't like it, don't worry about it. You can press dislike. I would urge you to press it twice to show me your extra disappointment. And please leave a comment, because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.